In the vast cold depths of our solar system lies a mysterious, enigmatic world that's long puzzled astronomers and captured the imagination of countless space enthusiasts. Shrouded in an icy blue-green hue, this distant gaseous giant harbors secrets yet to be revealed. The enigmatic planet Uranus, often overshadowed by its more famous brothers Jupiter and Saturn, has so far eluded our understanding. As it embarks on its space journey, the James Webb Space Telescope, the most advanced space observatory ever built, has turned its gaze to this distant world, uncovering breathtaking new images of Uranus's rings and its atmosphere. The stunning clarity of the images, far superior to anything we've seen before, could change our understanding of this enigmatic planet and tell us about the mysteries hidden in the outer reaches of our solar system. But what makes Uranus so unique, and why has it remained a mystery for so long? How did the James Webb Space Telescope capture the elusive rings of this gas giant, and what can we learn from its revolutionary observations? Let's delve into the fascinating world of this distant, icy planet and explore the secrets of Uranus that may hold the key to unlocking some of the most intriguing questions about our cosmic neighborhood. The James Webb Space Telescope represents a groundbreaking step forward in our ability to explore the cosmos. By orbiting the Sun at a distance of 1 million miles from Earth, the JWST offers tremendous opportunities to observe a wide range of celestial objects, including exoplanets, dying stars, and newborn galaxies. Our Uranus has not been overlooked. Its sophisticated instruments such as the near-infrared camera or NIRCam and coronagraph technology have already provided us with remarkable insights into the mysterious world of Uranus, and they could revolutionize our understanding of the universe. JWST's powerful instruments produce detailed images of distant celestial objects with unprecedented accuracy. Its NIRCam is specifically designed to detect faint, distant objects by blocking light from nearby brighter objects using a coronagraph. This advanced technology allowed JWST to take the sharpest images of Uranus's elusive dust rings. The telescope also managed to photograph the planet's polar cap, a unique white spot that appears and disappears as the seasons change, and even clouds probably associated with storm activity on the planet. Uranus, the seventh planet from the Sun located on the outskirts of the solar system, is a striking and mysterious sight that's long fascinated astronomers and space enthusiasts alike. This gas giant stands out among its neighbors with its unique blue-green hue, hinting at the complex and intriguing processes that govern its atmosphere. But what exactly is Uranus's atmosphere made of, and why does it have such a fascinating color? Uranus's atmosphere contains mainly hydrogen and helium, similar to other gas giants in the solar system like Jupiter and Saturn. But it's the presence of a third, more peculiar component that distinguishes Uranus from the others and gives it its characteristic appearance: methane. Methane is a gas composed of 1 carbon atom and 4 hydrogen atoms. It's present in trace amounts in Uranus' atmosphere, but it plays a crucial role in determining the planet's appearance. Uranus's unique blue-green color is the result of methane's ability to absorb the red wavelengths of sunlight. When sunlight passes through the planet's atmosphere, methane molecules absorb red light, allowing only blue and green wavelengths to reflect into space. This process leads to the stunning blue-green hue we observe when we look at the planet. Uranus's atmosphere is also characterized by a thick layer of haze that extends far above the planet's cloud tops. This haze, which is thought to be composed of hydrocarbon particles, further contributes to the planet's mysterious appearance by scattering sunlight and creating a soft glow. As if Uranus's charming blue-green appearance wasn't enough to distinguish it from other planets in the solar system, this distant world also boasts a unique rotation and tilt that's long puzzled astronomers. The way Uranus rotates on its axis and how it revolves around the Sun is unlike any other planet in our cosmic neighborhood, leading to some truly unusual phenomena and raising questions about its turbulent past. While most planets rotate around an axis that's more or less perpendicular to the plane of their orbit around the Sun, Uranus is the exception. Its axis of rotation is tilted at an extreme angle of 98 degrees, causing the planet to essentially roll in its orbit. This extraordinary tilt has a profound effect on the changing seasons and dynamics of the planet's atmosphere, creating a unique environment that challenges our understanding of planetary behavior. As Uranus revolves around the Sun, one of its poles is bathed in uninterrupted sunlight for long seasons, while the other is turned to the darkness of deep space. Each pole experiences one long day and night that last about 42 Earth years, and each season on Uranus lasts about 21 Earth years. The extreme seasonal variations combined with the planet's unusual rotation result in complex and dramatic weather patterns and atmospheric circulation. These factors cause storms and clouds to form on Uranus, leading to some truly amazing and mysterious phenomena. One of the most striking features of Uranus's atmosphere is the presence of large, bright cloud formations. These clouds are often associated with storm activity. Most recently, on February 6 of this year, the James Webb Space Telescope camera managed to capture such activity during a 12-minute exposure. The image shows two prominent clouds, one at the upper left of the polar cap, and the other at the far left edge of the photo of the planet. Cloud formations on Uranus are thought to consist mainly of methane ice crystals, which form at high altitudes in the planet's atmosphere. The methane clouds are then carried away by strong zonal winds that circulate around the planet, sometimes reaching speeds of up to 560 miles per hour. The interaction of these winds with the planet's complex atmospheric circulation patterns can cause large convective storms, which manifest as bright cloud formations. Uranus also has one striking feature characterized by a bright white spot near one of its poles, the polar cap. The polar cap of Uranus is thought to be a seasonal phenomenon, appearing on the planet in summer and disappearing with the onset of autumn. This bright white detail, visible in recent images taken by the James Webb Space Telescope, is located at the sun-drenched pole of Uranus. One possible explanation for the formation of the polar cap is that the result of extreme seasons on the planet and prolonged exposure to sunlight. Intense and continuous sunlight at the pole could cause the upper layers of the Uranus atmosphere to heat up, causing chemical reactions that produce reflective particles such as crystalline ice or hydrocarbon aerosols. These particles could then accumulate near the pole, forming the bright white polar cap that we observe. Michael Merrifield, an astronomer at the University of Nottingham, expressed surprise at the level of detail obtained by the James Webb Space Telescope, which was previously only possible during the Voyager 2 flyby. He explains, quote, "Unlike Voyager's flyby, we will be able to monitor its appearance over time, to see what effect its strange upside-down rotation might have on its weather conditions." The origin of Uranus's strong tilt remains one of the most intriguing mysteries of planetary science. One of the leading hypotheses is that the planet experienced a colossal collision with a protoplanetary body early in its history, which caused it to tip over on its side. Now, this catastrophic event would have had a lasting effect on the planet's rotation and may have played a role in shaping its unique atmospheric dynamics. The intriguing ice giant of our solar system fascinates us, not only by its unique atmosphere and inclination, but also by the fact that it's accompanied by a diverse and fascinating collection of satellites. With a total of 27 known satellites, each with its own distinctive characteristics, Uranus boasts an unusual celestial family that's long been the subject of scientific curiosity and research. These satellites are named after characters from the works of William Shakespeare and Alexander Pope, and they're divided into three main groups. Inner satellites, large classical satellites, and irregularly shaped outer satellites. Each group exhibits a wide range of sizes, compositions, and surface features, adding complexity and fascination to the Uranus system. This stunning image taken in February not only shows the beauty of Uranus, but also shows 6 of those 27 satellites. In addition to the breathtaking picture, a background of distant galaxies can be seen, further emphasizing the immense and impressive nature of our universe. The inner satellites, which include Cordelia, Ophelia, Bianca, Cressida, Desdemona, Juliet, Portia, Rosalind, Cupid, Belinda, and Perdita, are small satellites orbiting in close orbit and are mostly composed of water, ice, and rocks. These satellites are thought to have formed from the remnants of a massive collision or from the same primary material that coalesced to form Uranus itself. The classical satellites, consisting of Miranda, Ariel, Umbriel, Titania, and Oberon, are larger and more massive than the inner satellites, making them the best-known satellites of Uranus. These satellites exhibit a fascinating range of geological features, such as canyons, rocks, impact craters, and possible cryovolcanoes, providing us with valuable information about the dynamic processes that have shaped their surfaces over time. Finally, irregularly shaped outer satellites are a group of small distant satellites with elongated and highly inclined orbits. These satellites include Caliban, Sycorax, Prospero, Setebos, Stefano, Trinculo, Francisco, Margaret, Ferdinand, and others, and are thought to be captured objects, possibly originating in the Kuiper Belt or beyond. Their irregular orbit and diverse composition suggest a chaotic past involving collisions and gravitational interactions with other celestial bodies. While the diverse family of satellites of Uranus continues to capture our attention, we cannot lose sight of another important aspect of this distant ice giant. Surprisingly, the planet is home to an outstanding ring system that's remained largely hidden from our view until now. Unlike the bright, dazzling rings of Saturn, which have attracted the attention of star watchers for centuries, the rings of Uranus are more subtle and elusive, their secrets hidden in the darkness of space. So what are these mysterious rings made of? And what makes them so strikingly different from the features we observe around other planets in our solar system? One of the most striking aspects of Uranus's rings is the unique arrangement and structure. In contrast to Saturn's wide, fuzzy rings, Uranus's rings are relatively narrow and compact, forming distinct bands around the planet. This unique configuration has long puzzled astronomers who've tried to understand the forces that shape these mysterious features. The rings of Uranus are mostly composed of small rock and dust particles that absorb rather than reflect sunlight, making them much darker and less visible than those icy rings of Saturn. These elusive faint rings were first discovered in 1977, but it wasn't until the Voyager 2 spacecraft flew by in 1986 that we were able to get a closer look at their composition and structure. Voyager 2, launched in 1977, was the first spacecraft to provide us with close-up images of Uranus and the rings during its historic flyby in 1986. During its brief approach to the planet, Voyager 2 took pictures of the brightest and most prominent rings, providing us with valuable information about their composition and structure. However, the limited resolution and sensitivity of Voyager's 2 instruments meant that it could observe only the most visible details, leaving the faintest and most distant rings shrouded in mystery. The Keck Observatory, located in Mauna Kea, Hawaii, has also played a crucial role in advancing our understanding of Uranus's rings. Equipped with powerful telescopes and advanced adaptive optics technology, the Keck Observatory was able to observe some of Uranus's fainter rings from Earth. However, even with the impressive capability of the Keck Observatory, a detailed study of the faintest rings of Uranus remained a challenge because of the limitations of ground-based observation. The James Webb Space Telescope, with its unprecedented sensitivity and powerful capabilities, has now bridged the gap between previous observations and has provided us with the clearest and most detailed image of Uranus's rings to date, including those that remained elusive for both Voyager 2 and the Keck Observatory. Webb's stunning images show 11 of the 13 known rings of Uranus, including 2 of the dimmest and most elusive. So how did Webb manage to capture these faint, elusive rings when they remain hidden from so many other telescopes throughout history? The exceptional sensitivity of the NIRCam that we already mentioned allowed it to pick up the dim light reflected from the dark rocky particles that make up Uranus's rings, which would otherwise be invisible to most telescopes. And using the coronagraph to block out the intense light of Uranus itself, Webb was able to detect faint dust rings that had previously been hidden due to the planet's overwhelming brightness. A stunning image of Uranus's rings was taken while the Earth was 1.83 billion miles away from Uranus. This long exposure allowed the telescope to collect enough light from the faint rings to produce a clear and detailed image, revealing details never before observed with such clarity. The progress from Voyager 2 to the Keck Observatory and now to the James Webb Telescope, it demonstrates the power of innovation and technological advances in astronomy. As the James Webb Space Telescope continues its mission to unlock the secrets of space, its advanced capabilities promise to usher in a new era of astronomical discovery. As we continue to push the boundaries of our understanding and explore the mysteries of the universe, the combined efforts of past, present, and future missions could change our understanding of the world and our place in it, from distant galaxies that hold clues to the early universe to the mysterious ice giant Uranus. More than 30 times farther from the Sun, almost at the edge of our solar system, there's one mysterious planet, Neptune. It's impossible to see it, even from the highest points on Earth without a telescope. Because of its remoteness, Neptune is the least explored planet in our entire system. But what could be so mysterious about this planet? Would you be surprised if we told you that Neptune, one of the coldest planets in the system, can support an ocean of superhot water? Today you'll learn about that, as well as Neptune's strange rings, what makes it so blue, and also what is now known about its famous satellite, Triton. Neptune is an ice giant, about 4 times wider than Earth. It has a radius of about 15,300 miles, and a volume of 15 trillion miles cubed, which means that Neptune is 58 times larger than Earth in volume. The planet is composed mostly of water, methane, and ammonia. Like the other ice and gas giants in our system, Neptune has no solid surface. Its atmosphere extends deep into the planet to the mantle, which is composed of methane and ammonia ice, and a rocky core. Nevertheless, scientists believe that the ice giant could theoretically have an internal hot ocean. But how can a planet sustain such an ocean since it's so far from the Sun? It would take sunlight 4 hours to reach the giant's surface. Neptune's average atmospheric temperature is negative 360 degrees Fahrenheit, making it one of the coldest objects in the solar system. In addition, according to recent research, most of Neptune cooled from 2003 to 2018, despite warming near the South Pole from 2018 to 2020, likely due to seasonal changes in atmospheric chemistry. The reason for the likely formation of the ocean inside the ice giant remains unsolved. However, scientists suggest that this strangeness can be explained by internal heating. Heat released due to gravitational compression or gravitational interaction between Neptune and one of its satellites, Triton. On the other hand, researchers Sloan Viktorovich and Andrew Ingersoll believe that the probability of oceans on Neptune due to its heat is very low, only 15% at this time. According to scientists' calculation, only in 1 billion years will the chance of an ocean there increase to 40% after the giant cools down. Another explanation for the huge internal energy could be Neptune's collision with some cosmic object, because Neptune is the only planet that emits nearly 3 times as much energy as it receives from the Sun. This is also confirmed by the unusual 28-degree tilt axis, almost as much as on Earth. Because of this, Neptune also experiences seasons similar to ours, but on Neptune, one season lasts about 40 years. 1 year for Neptune is 165 Earth years, yet 1 day on the ice giant takes 16 hours. This rapid rotation of the planet creates super powerful wind, which we'll talk about a little later. Neptune's atmosphere is 80% hydrogen. It also contains 19% helium and about 1% of other gases, including methane. By the way, Neptune's blue color is caused precisely by methane clouds in the upper layers of the atmosphere. Methane molecules can absorb solar shortwave radiation, reflecting the blue color. However, the nearest planet to Neptune, Uranus, also contains a similar distribution of gases. But unlike Neptune, the color is pale blue. Dr. Patrick Irwin of Oxford University suggests that this color difference may be due to the density of methane fog. Thus, the atmospheres of both planets have several aerosol layers. The bottom deep layer consists of a mixture of hydrogen sulfide ice. It's because of this layer that some areas can be seen closer to the poles. For example, they appear darker on Neptune. The second layer is probably just what affects the colors of the planets. It's a layer of haze particles in which methane ice probably forms. The ice then precipitates as a rain of methane snow, since Neptune's atmosphere is much more active than that of Uranus. Neptune forms this snow more efficiently, so its second aerosol layer is thinner. It is precisely the lower density that causes this rich blue color. The last third atmospheric layer also forms large particles of methane ice and is, in fact, an extension of the second layer. In addition to its intense color, Neptune is also characterized by dark and white patches all over its surface. All of these spots are storms resulting from the planet's very rapid axial rotation. Neptune is the windiest planet in the system. Wind currents there can reach 1,200 miles per hour, which is almost 4 times stronger than Jupiter. However, the ice giant has one similarity with Jupiter, a huge storm. The name of this vortex is simple enough: the Big Dark Spot. The Earth-sized cyclone orbiting at 1,500 miles per hour was first detected by the Voyager 2 spacecraft in 1989. However, in 1994, another telescope, the Hubble, noticed the spot had disappeared and a small, new spot appeared in the northern hemisphere. So unlike the 300-year-old cyclone on Jupiter, Neptune's large-scale vortices only exist for 2 to 6 years. In 2018, Hubble detected another new spot, similar to the one discovered in 1989. The formation of these storms is still unknown, but scientists suggest they originate deep in the atmosphere, forming over several years. These storms still have something to show scientists. The new 2018 spot began drifting southward the following year, where it would have disappeared. However, unexpectedly for researchers, the storm turned around and began moving back north. What's more, a small one probably separated from the big spot. NASA scientists believe the small vortex may be part of the process of breaking up the big storm, which has never been observed before. Such cyclones in previous observations have been accompanied by white methane clouds, called scooter, because of the speed of motion greater than that of the big spot. They probably form over vortices, where gases freeze into ice crystals. The lack of clouds, the researchers say, may help in understanding the formation of patches on Neptune and similar ice giants. Like other gas giants, Neptune has another feature, a ring system. In 2022, the James Webb Space Telescope took a near-infrared image of the icy giant, showing its faint rings and satellites. The last image of Neptune's rings was taken more than 30 years ago by Voyager 2. In Webb's new photo, about 5 rings can be seen. All rings are named after astronomers who have contributed to the study of Neptune. The closest and most loose ring is called Halley. It consists of about 40% to 70% dust and is 26,000 miles and has a radial width of 1,240 miles. The second ring of Leverrier is much brighter, but much narrower. Its width is a little over 62 miles. The next ring is the widest of all. This is the Lassell ring, 2,485 miles wide. The percentage of dust there is very small, ranging from 20% to 40%. The fourth, Arago ring, is hard to see. It is one of the smallest rings with a radius of 35,540 miles. And it's on the edge of the Lassell, and probably because of its low dust content, is hardly noticeable. The last, Adams ring, has an orbital radius of approximately 39,724 miles. Moreover, Adams is only 35 kilometers wide, making it the narrowest ring of Neptune. But what makes this ring stand out in its arcs? The arcs are mysterious bright seals of dust around the perimeter of the ring. Each of Adam's arcs has a name: freedom, brotherhood, courage, and equality. Interestingly, they are not static at all. These arcs, especially brotherhood and equality, exchange their material and change their size. Why these arcs formed is still unknown, but researcher Imke de Pater suggests that the cause may be the collapse of a parent companion or other object in the Roche limit. In addition to the rings, Webb also recorded 7 of Neptune's 14 satellites. All of the ice giant's moons are divided into regular and irregular. Webb captured 6 ordinary inner satellites. Some of these satellites, like Despina and Galatea, form Neptune's rings, playing the role of shepherd for dust. However, definitely the most interesting thing in Webb's image is the most distant bright satellite, Triton. In the photo, Triton looks like a star because it glows much more than Neptune. The strange glow is because the satellite is almost completely covered by nitrogen ice, and therefore reflects about 70% of all sunlight that falls on its surface. Triton is Neptune's largest satellite. It is larger even than Pluto. It has a diameter of 1,680 miles, which can be equated to 99.7% of the mass of all Neptune's moons. It is also the coldest geologically active object in the entire solar system. Its surface temperature reaches negative 391 degrees Fahrenheit just because of its light-reflecting, icy surface. Like any of the moons of the ice giant, Triton experiences wave blocking, meaning that only one side of it is turned toward the planet. However, its retrograde orbit sets it apart from other satellites, which is unusual and unique to all other satellites in our system. That means that Triton has an inclined orbit, which causes it to move in the opposite direction to Neptune. Also, because of this orbit, its poles and equator alternately face the Sun. But what could have caused such an unusual orbital tilt? Most likely, Triton never formed with Neptune. Scientists believe that Triton originally evolved in the Kuiper Belt, but at some point it was able to be captured by an ice giant, and it's assumed that Triton could hypothetically move around another object. Therefore, the captured Triton slowed down, which prevented it from colliding with Neptune. Moving toward Neptune, the satellite could also destroy other moons. Neptune has very few satellites compared to, for example, Jupiter, around which there are almost 70 objects. There probably could have been more, and they would have been larger had not Triton been captured by the giant's gravitational pull. Triton's features don't end there. If you look closely at pictures taken back in 1989 by Voyager 2, you can discern the satellite's unusual mosaic surface, modeled with plumes. According to the analysis of the craters by scientists, their surface could be from 10 million to 100 million years old, and in some places, the smooth surface on the manifestation of cryovolcanism. Therefore, scientists believe that the moon may have a subsurface ocean. The plumes also probably hint at this and also depict a depression similar to a lake basin. Despite its low temperature, Triton probably retains a lot of ammonia beneath its surface, which slows the freezing of the water. On the other hand, plumes may appear due to heating by sunlight, causing nitrogen to compress beneath Triton's icy surface until the nitrogen escapes. At this point, proving that the satellite could be an oceanic world is very difficult. In addition, solar heating probably forms the moon's thin nitrogen atmosphere. However, the possibility of life developing there, as on presumably Enceladus, is too early to tell. Given that Triton was part of the Kuiper Belt, does this mean that Neptune can influence its objects? The Kuiper Belt is the boundary of our solar system, also the comet's source. The belt extends from Neptune 30 AU by about 20 AU. The belt is predominantly composed of small objects like asteroids and tens of thousands of more large objects, including dwarf planets like Pluto. Were it not for the gravitational influence of an ice giant, it's likely that a planet could have formed from the Kuiper Belt. In addition, scientists have noticed that some objects in the belt, including Pluto, are in long-range resonance with Neptune. Usually such objects, planetesimals, can only temporarily come into resonance with a stable, fixed-in-one-place planet. Therefore, scientists suggest that it's likely that Neptune may have migrated from the inner regions of the solar system, meaning that it may have originally formed close to the Sun. Thus, the migration of the ice giant was probably able to keep many Kuiper Belt objects within the solar system, when, without resonances, gravitational effects could have pushed them outside the system and even in our direction. Neptune definitely has many unexplored mysteries. At this point, we don't know, for example, the exact composition of Neptune's interior, or in general how ice giants are formed. So, we have to wait for future scientific expeditions that will help us better understand the chemistry of these worlds and unravel many of the mysteries that interest us. Have you ever wondered if some of the most exciting scientific discoveries can be made from data stored for decades? That's exactly what happened when NASA's Magellan spacecraft took pictures of Venus more than 30 years ago. At the time, scientists were focused on mapping the planet's surface and studying its dense atmosphere. But what they didn't realize was that they were capturing something far more extraordinary. Images taken more than 30 years ago led to a sudden discovery. Beneath the dense, poisonous clouds of Venus, all this time lay a great fire secret: active volcanoes. This groundbreaking discovery changes our understanding not only of Venus but also of other planets in our solar system and beyond. Venus, the second planet from the Sun, is often called Earth's evil twin because of its similar size and composition. However, while Earth is a refuge for life, Venus is a planet of extremes. With a diameter of about 7,521 miles, Venus is almost the same size as Earth, but it's much closer to the Sun, with an average distance of about 67 million miles, which is about 1/8 closer than our home planet. This proximity means that Venus has a much hotter environment than Earth, with surface temperatures that can reach 880 degrees Fahrenheit. This makes it the hottest planet in our solar system, even hotter than Mercury, which is much closer to the Sun. One of the key factors contributing to Venus's high temperatures is its dense atmosphere, consisting mostly of carbon dioxide and nitrogen. This atmosphere creates a powerful greenhouse effect, trapping heat and causing temperatures to rise. In addition, the dense clouds of sulfuric acid that envelop the planet contribute to its intense heating. Despite its harsh conditions, Venus has long fascinated scientists who have sought to study its unique characteristics and understand its history. Over the years, researchers have made many discoveries about Venus, including the fact that it is the only planet in our solar system that rotates clockwise on its axis. Moreover, the atmosphere of Venus is dominated by the rapid rotation of the cloud layer, which rotates much faster than the planet itself. This zone rotates in just 4 Earth days, while the planet itself takes a leisurely 243 days to complete a full rotation. Both rotations occur in retrograde direction, defying the norms of the solar system. In the context of Venus, this means that the planet and its atmosphere move in a direction opposite to the rotation of the Sun and most other planets in the solar system. Now, this natural convectional motion, known as superrotation, begins at about 6 miles and steadily increases up to 40 miles, where the equatorial winds reach a terrifying speed of 335 miles per hour, gradually slowing down as they climb to higher altitudes. It seems that the atmosphere of Venus, or at least the cloud layer, rotates about 50 times faster than the planet itself, and this fascinating phenomenon probably influenced the rotation of the planet. But here's the catch. The mass of Venus's atmosphere is only 1/10,000th of the planet's mass. So how could that be? There must have been an exchange of velocities between the planet and the atmosphere to conserve total kinetic energy. The mystery remains unsolved. Also, despite the planet's scorching heat and harsh environmental conditions, the temperature on the planet's surface is almost constant and uniform due to the winds that sweep across its surface and ensure that heat spreads evenly. During the Venusian night, which lasts about 58 Earth days, the surface temperature drops only slightly. However, the temperature changes with altitude. The atmosphere at 62 miles ranges from positive 81 degrees Fahrenheit during the day to negative 225 degrees Fahrenheit at night. Venus's atmosphere is massive, more than 100 times the weight of the Earth's atmosphere. The huge mass of Venus's atmosphere also has great thermal inertia, which largely explains the homogeneity of the temperature on the planet's surface, in which one can observe an analogy with the water of Earth's oceans. Venus's atmosphere has a density of about 1/10 the density of water, which together with the corrosive composition of the atmosphere is responsible for a level of erosion comparable to a river. For all that, there's almost no wind at the planet's surface, barely exceeding the speed of a few miles per hour, being stronger at the equator and weaker toward the poles. They create a visible V-shaped structure in cloud layer images. However, much of Venus's prehistory remains a mystery. For example, although it's known that the planet formed about 4.5 billion years ago, it's unclear how it evolved to become the hot, hostile world we know today. Some scientists speculate the volcanic activity may have played a significant role in the shaping of the planet's environment, with eruptions releasing gases that contributed to the dense atmosphere we see today. Over the years, scientists have made many observations of Venus from both Earth and spacecraft. Some of the earliest recorded observations date back to ancient times, when astronomers such as the Greek philosopher Pythagoras and the Roman poet Ovid documented their observations of Venus in the night sky. However, it wasn't until the 20th century that scientists were able to study Venus in more detail. In 1961, the Soviet Union launched the first spacecraft to visit Venus, called Venera 1. Although the spacecraft could not successfully land on Venus, it provided valuable data on the planet's magnetic field and radiation environment. Subsequent missions, including the Soviet Union's Venera and Vega missions and the U.S. Mariner and Magellan missions, provided even more detailed data on Venus. Despite these successes, however, the study of Venus has proven to be a major challenge for scientists. The planet's dense atmosphere makes it difficult to see its surface, and its harsh conditions make it difficult for spacecraft to exist for long periods of time. The Soviet Union's Venera 13 landing module, which successfully landed on Venus in 1982, lasted only about 2 hours before falling victim to intense heat and pressure. NASA's Magellan spacecraft arrived at Venus in 1990 and spent 4 years mapping the planet's surface with radar. The spacecraft collected an enormous amount of data, including detailed images of the planet's surface and data on its topography, gravity, and magnetic fields. Only more than 30 years later, in 2021, scientists made an incredible discovery when they reanalyzed the data collected by Magellan: the presence of active volcanoes on Venus. The discovery was made by a team of researchers led by Anna Gilcher of the Institute of Geophysics at the Swiss Federal Institute of Technology in Zurich. The researchers analyzed Magellan radar data and identified features on the surface of Venus that suggested the presence of recent volcanic activity. The team also examined images taken by the spacecraft and found evidence of lava flows and other volcanic features. But how did scientists determine the presence of active volcanoes on Venus from data collected more than 30 years ago? One key factor was the use of new imaging techniques and algorithms that allowed researchers to extract more detailed information from the data collected by Magellan. By analyzing radar data, the researchers were able to identify changes on the surface of Venus that were probably caused by volcanic activity. They also found evidence of elevated surface temperatures in the same locations, further supporting the idea that there are active volcanoes on the planet. Moreover, quite recently, in March of this year, scientist Robert R. Herrick of the Geophysical Institute, University of Alaska Fairbanks, and Scott Hensley of the Jet Propulsion Laboratory, California Institute of Technology, conducted a similar study. In an article in Science, They discussed how volcanic activity on Venus has been obscured by the lack of observable eruptions. However, the authors used images from the same Magellan spacecraft to study volcanic areas on Venus. Thanks to images taken between 1990 and 1992, a manual search was conducted in areas previously identified as probable manifestations of active volcanism. The authors searched for volcanic formations like cones, vents, and lava flows that had appeared or changed between images. To create a detailed topographic map, they used a technique called stereo radar-grammetry. They also made the images look as if they had been taken directly over the observation object, using a process called orthogonal transformation. The paper also describes a direct simulation, distant view of images of the appearance of surface objects at different viewing geometries, which were then compared with similar versions of the images. As a consequence, they found that the vent of a volcano in the Atla Regio region had changed dramatically in less than a year. The same opening doubled in size and became deformed, with a lake of lava filling the edge 8 months later. This discovery may provide insight into the evolution of Venus and the differences between its landscapes and that of Earth, since it was originally thought that the surface of Venus, like that of Earth, had water. However, it's not entirely clear whether volcanism is currently active or not. The low level of detection suggests that Venus is less volcanically active. Even Jupiter's satellite Io, only about 1.5% of the surface area of Venus has been studied, given the missing and poor data. The recent discovery of active volcanoes on Venus is a breakthrough of great importance to the field of planetary science. One major implication is that it challenges the common view of Venus as a geologically dead planet. The presence of active volcanoes means that Venus is still geologically active, which opens up new possibilities for studying the formation and evolution of the surface of rocky planets. Another potential consequence of the discovery of active volcanoes on Venus is the possibility of detecting microbial life on the planet. Volcanic activity on Earth is often associated with the presence of microbial life, and the same may be true on Venus. Although conditions on Venus are harsh, a temperature is high enough to melt lead and a dense atmosphere of carbon dioxide, it is possible that microbial life may have adapted to survive in those extreme conditions. As for future research missions, the discovery of active volcanoes on Venus has already generated considerable interest among planetary scientists. There are plans for future missions to Venus, such as the Veritas and Da Vinci Plus missions. The Veritas mission is led by NASA's Jet Propulsion Laboratory and will be launched within a decade to study Venus from its surface to its core, to understand how a rocky planet the size of Earth took an entirely different path. The Veritas mission will use the state-of-the-art synthetic aperture radar to create three-dimensional global maps and a near-infrared spectrometer to determine surface composition. The spacecraft will also measure the planet's gravitational field to determine the structure of Venus's interior. The Da Vinci Plus mission, on the other hand, is a complement to the Veritas. NASA plans to launch it to study the atmosphere and geology of Venus. While the Veritas orbiter will orbit Venus and capture data from the above, the Da Vinci descending sphere will descend through Venus's atmosphere to measure its composition as well as study clouds, winds, and surface features of the planet. The sphere will also capture high-resolution images of Venus's surface as it descends, providing valuable information about the planet's geology and geophysics. Unfortunately, there have not been many missions to Venus in the last 30 years. In fact, funding for planetary exploration has been cut, and new missions to Venus will not start until the 2030s. But with each discovery, we're one step closer to unraveling the processes that shaped our own planet Earth. In addition, The study of Venus provides valuable information about exoplanets outside our solar system, because many exoplanets are similar to Venus. Studying this planet can help scientists determine the potential habitability of other worlds. The recent discovery of active volcanoes on Venus is just the tip of the iceberg, but it underscores the importance and complexity of studying and analyzing large amounts of old data. Although this is just one event, the data may contain other discoveries waiting to be revealed. It is important to note that tools for processing and comparing large amounts of data were not available until recently. This provides a huge field for anyone interested in astronomy or planetary science to conduct their own research and make discoveries. Even without expensive equipment, anyone can contribute to this field by working hard and with dedication. The solar system is unique 20 to 30% of the time. In similar planetary constellations, the central star absorbs the planets that revolve around it. But if that's the case, why didn't this happen to us? The answer to this question may lie in the largest and oldest planet of the solar system, Jupiter. It is possible that before Earth, Venus, and Mercury there have been other planets. However, they may have been destroyed by Jupiter, laying the foundation for the current solar system. In fact, what if we told you that Jupiter might have originated outside of our star system? Today we'll talk about the hypothetical migration of the gas giant, as well as the way this may have affected life on Earth. As you know, Jupiter is a huge planet composed entirely of gas, mostly helium and hydrogen. The first studies of Jupiter took place back in the 17th century. However, many aspects in regards to this planet remain unsolved to this day. For example, Jupiter's most notable feature, the Great Red Spot or GRS, is still controversial in scientific circles when it comes to its origin, length of existence, and color. Jupiter's rapid rotation around its axis, approximately 9 Earth hours, creates lengthy and powerful cyclones and anticyclones that can reach speeds of 335 miles per hour. The Great Red Spot is an anticyclone that has been around for over 300 years. However, the GRS is decreasing. According to NASA, in the 19th century, the size of the anticyclone was estimated to be 25,500 miles in width, but now it is slightly larger than the diameter of Earth, 10,250 miles. The reason for the size decrease of the GRS is still unclear, but NASA scientists suggest that the answer may be some unknown activity in Jupiter's atmosphere, which weakens the wind currents. Another mystery of the GRS is the signature red hue. NASA scientists suggest that the cause of the redness is a little-known colorless gas, ammonium hydrosulfide, and it forms sulfur when exposed to solar UV. What's more, NASA scientist Amy Simon believes that there's a correlation between the intensity of the storm's color and its speed. According to her research, the color of the GRS becomes more saturated when the wind speeds up. In addition to helium and hydrogen, Jupiter's atmosphere contains heavy elements such as nitrogen, argon, xenon, etc. However, these elements could only form at very low temperatures where they mixed with other elements that occur in hot environments. This led scientists to the conclusion that perhaps Jupiter did not originate in the same place that it now occupies in the solar system. This gas giant could have theoretically formed 4 times farther away from the Sun. Jupiter might have been enriched with heavy elements and then headed towards our star, completing its formation. To understand the possible migration of Jupiter, let's take a closer look at how gas giants are formed. Gas giants form in a similar way to ordinary planets, but with a few differences. After a star is born from gas and dust clouds, the excess material rotates around the star, kind of like giant planetary rings. These rings are known as the protoplanetary disk. This is what the planets are formed from. On average, a protoplanetary disk only exists for a very short time on a cosmic scale, up to 10 million years. The disk consists of 99% gas and only 1% dust. As the dust particles crash into each other, thanks to gas, they stick together and form larger objects known as planetesimals. As they continue to gain mass, planetesimals eventually become planets, asteroids, or moons, depending on the amount of material. Planets with a solid surface are formed closer to the star. This is due to the fact that the radiation released after the birth of the star, it can't push heavy elements that make up the planets like the stone and metal very far. Gas giants form away from the star as radiation can push the gas farther away. However, a lot of gas is not enough to become a gas giant. These planets must also have a massive solid core to attract gas. So how do the gas giants form such large nuclei if the building materials do not reach them in the quantities they need? According to the research of astrophysicists Kobayashi and Tanaka, these giants can build up large core mass thanks to pebbles that are pulled into the solar system due to the orbit of Neptune. Additionally, the ice particles that are pushed out by radiation as vapors can act as a building material for the core. Finally, it is possible for gas giants to be born outside the planetary system and then migrate into narrow orbits. The hypothesis of such planetary migration is called the Grand Tack hypothesis. The Grand Tack hypothesis by Kevin Walsh of the Southwest Research Institute in Boulder suggests that Jupiter likely originated much farther away from the Sun than its current position and gained its mass as it migrated toward the Sun. Also, this hypothesis suggests the migration of Jupiter may have caused the emergence of the asteroid belt and even the insufficient mass of Mars. According to a study by a team of astronomers at Lund University, the future gas giant may have potentially originated in the outer region of the solar system as an icy asteroid. After 2 to 3 million years, Jupiter likely accumulated a mass almost equal to our planet and began to shift towards the Sun. Researcher Shoshibata explained that Jupiter may have been about 20 AU from the Sun when the solar system was first formed. Affected by gravity, the gas giant headed towards the Sun. On its journey towards the Sun, Jupiter likely chose a very successful path, which was filled with the material necessary for its development. The streams of gas that were still orbiting the newborn Sun were most likely picked up by Jupiter. The gas giant went in a spiral and took a total of about 700,000 years. Hypothetically, Jupiter may not have been in the same place where it is now. The gas giant potentially occupied the current place of Mars. Over time, Jupiter must have migrated to the new space it now occupies in the solar system. A likely proof of Walsh's hypothesis is a group of asteroids called Jupiter Trojans. These asteroids surround the planet from two sides, the front and the back. While exploring these mysterious asteroids, scientists have been very puzzled as to why the group of Trojans in front of Jupiter is twice as large as the one behind. Thanks to computer simulations, scientists at the University of Lund in Sweden have concluded this is asymmetry and is probably caused by planetary migration. Based on that hypothesis, during the internal migration, Jupiter's gravity widened the particle path, securing more Trojans in front of it. Scientists suggest that the Jupiter Trojans may have been part of the Kuiper belt, which is located beyond the orbit of Neptune. These asteroids have the potential to allow scientists to explore materials left over after the birth of the solar system without sending spaceships that far. Naturally, these significant space maneuvers of a giant planet could not have left our solar system unaffected. The most compelling evidence of the grand tack is Mars. It's possible that without the intervention of Jupiter, the red planet would have been larger than Earth. Mars was formed around the same time as Jupiter, so it had the time and opportunity to accumulate a significant mass. However, Mars is only about 4,225 miles in diameter, and for reference, the diameter of the Earth is 7,955 miles. So Mars is about half the size of our home planet. Jupiter is most likely to blame for this. When the gas giant got close to the Sun, it may have absorbed or dispersed the materials that were intended for Mars towards Earth and Venus. Jupiter's mischief doesn't end there. There is an asteroid belt between the orbits of Mars and Jupiter. It covers approximately 140 million miles. The belt mainly consists of small asteroids, although it also contains several larger bodies. For example, there's a dwarf planet Ceres, as well as large asteroids up to 400 miles across, including Vesta, Pallas, and Hygeia. It is possible that another planet could have formed from this belt. However, according to the grand tack hypothesis, its formation may have been prevented by the gravitational forces of Jupiter. Because of the gas giant, the planetesimals were not able to unite and simply fell apart. It's possible that Jupiter may have also dispersed a significant amount of materials in the process of migration. Therefore, even if it were possible to switch off the influence of Jupiter, the mass of the belt would not be sufficient to form even a small planet similar to Mars. Finally, the least apparent but most significant consequence of Jupiter's migration was the likely destruction of the first planets in our system. The solar system is really different from other systems. Many of the known planetary systems similar to ours have super-Earths in their composition. These planets are larger than Earth and consist of either rock or gas or a combination of both. So why don't we have planets like that in our system? Astronomer Konstantin Batygin suggests that such planets may have existed in the early days of the solar system. However, it's possible that Jupiter destroyed the first generation of planets. The gravitational influence of Jupiter, which hypothetically traveled close to the Sun and then back to current orbit where it is now, led to the collision of the forming planets. In fact, Jupiter may have set the stage for the formation of the planets we know and, of course, the planet we live on. However, the formation of planets takes a very long time from humanity's point of view, several million years. Therefore, Mercury, Venus, and Earth continued to develop from an already slightly depleted protoplanetary disk. Delayed formation explains the small size and thin atmosphere, as well as the age difference between the outer and inner planets. Admittedly, it is possible that it was Jupiter that influenced the current structure of the solar system. The annihilation of the first planets and the obstruction of the development of Mars may sound like negative events. However, Jupiter's intervention may have had positive consequences for us. What if we told you that the gas giant's migration probably gave the opportunity for life to evolve on our planet? The mystery of the huge amount of water present on Earth is still unsolved in the scientific community. The oceans could not have come into being at the same time as our planet, since all water would have evaporated due to the very high temperature during Earth's formation. However, water probably existed inside our planet. but there was not enough of it to cover 70% of the Earth's surface. The small asteroids are considered to be the most likely source of water, having contained water in the form of ice. Over the course of its migration, Jupiter may have sent these asteroids in our direction. Moreover, according to astronomer Phil Plait, in addition to water, meteorites containing building blocks for living organisms, that's small asteroids that reach Earth, such as amino acids from which proteins are formed. Therefore, Jupiter may have been one of the reasons for the origin of life on Earth. In a way, Jupiter can even be considered our shield to some extent. The gravity of the gas giant can change trajectories of dangerous asteroids and comets, steering them away from Earth. And furthermore, Jupiter is capable of absorbing comets that have the potential to become a threat to other planets. For example, in 1994, the 1.2-mile comet Shoemaker-Levy 9 crashed into Jupiter. If this had reached Earth, all life on our planet would have been doomed. However, in order for water to exist on Earth as abundantly as it does now, Jupiter most likely sent asteroids in our direction. That is, Jupiter does not always protect us. On the contrary, it can also be a source of attack. Professor Jonte Horner of the University of Southern Queensland has determined that Jupiter increases the risk of asteroids colliding with our planet. Nevertheless, if Jupiter had a smaller mass, it would have dramatically increased the possibility of cosmic bodies reaching Earth. Therefore, Jupiter definitely plays an important part in our life, but it also has the potential to harm it. Interestingly, there's another subtle influence that Jupiter has on Earth. The Earth's orbit is almost perfectly circular. However, due to Jupiter's gravitational pull, it can stretch into an elliptical shape. This deformation of the orbit will lead to significant climate changes. The summers become much hotter, and the winters much colder. Of course, this does not happen very often, only every 405,000 years. But we're currently in the midst of that cycle. The migration of Jupiter has not yet been confirmed and requires further research. However, it's likely that without the gas giant, our solar system would be completely different. It is possible that without its influence, life on Earth may not have existed at all. In 2021, NASA sent the Lucy spacecraft to explore the Trojan asteroids. Perhaps its expedition will reveal more data to confirm the hypothesis of Jupiter's migration. It may also allow us to study the material from which our universe was formed more than 4 billion years ago. Mercury is the closest planet to the Sun, which on the face of it seems inanimate and completely uninteresting. However, despite its enormous temperature, there's water at its poles. Moreover, the surface of Mercury surprises all astronomical scientists. There are the rarest types of impact craters and even forms of relief unknown to modern science. Finally, although Mercury is very small, it has enough of a magnetosphere to protect its surface from supernova and even a minor atmosphere that should have been weathered by now. Today, we'll tell you about the mysterious Mercury, as well as the secrets of the surface of this small planet. Mercury has a radius of 1,516 miles and is on average only 36 million miles from the Sun, or about 2.5 times closer than Earth. Therefore, 1 year on the planet takes 88 days. The planet's temperature reaches 800 degrees Fahrenheit, but because of its very thin atmosphere, it can drop to negative 290 degrees Fahrenheit at night. By the way, Mercury rotates very slowly around its axis. One day on Earth would be 59 days on Mercury. That is, the day and night on the planet lasts for 3 months. What causes such a slow rotation? Mercury is not blocked by the tides of the Sun, as has been assumed for a very long time. It is in spin-orbit resonance with the star in a 3:2 ratio. It rotates around its axis 3 times in 2 revolutions around the Sun. It's thought that Mercury may have previously been in 1:1 resonance, but something, probably collision with a giant object, caused the spin rate to change, as hinted by its many craters, including the impact basin of Colorus. On the other hand, according to research, a group of scientists led by Benoit Noëls have concluded that Mercury may have been in such resonance almost from the beginning of its formation. Another important factor influencing the rotation and temperature of Mercury is its eccentric orbit. The planet's orbit is elongated and resembles an egg, so depending on its position, Mercury's distance from the Sun can range from 29 million miles to 43 million miles. Mercury's orbit has another peculiarity that was discovered only recently. The orbit holds a dusty ring of the planet. Scientists believe that Mercury was too small and close to the Sun to have a ring. Moreover, scientists were going to investigate the planet's orbit to find an area around the Sun that had no dust, but found a dust ring instead. The ring is very thin and 9 million miles wide. The source of the ring could be meteoroids and the dust cluster in the same orbit as Mercury. A group of scientists led by Dr. Peter Pokorny believes that such a phenomenon may not be unique, but common in other exoplanet systems, where different space objects constantly crash into planets without a significant atmosphere. Interestingly, despite its small size, Mercury has a magnetic field. Although its magnetic field is the smallest in the entire solar system and has only 1% of the strength of Earth, it's still capable of reflecting stellar winds off the surface, forming a magnetosphere. Nevertheless, the magnetosphere is probably leaky, that is, it has holes through which sunlight can penetrate. As it flew past Mercury, the Messenger Space Telescope noticed magnetic tornadoes on the surface, beams of magnetic fields connected to the interplanetary space field with rarefied gas and magnetic fields carried by the solar wind. These openings in the planet's magnetosphere allow us to replenish the barely detectable atmosphere. But we know that the magnetic field is formed by the movement of electric current in the liquid metal in the planet's core. Does Mercury have a core large enough to generate a magnetic field? In fact, Mercury's core is even 1/3 of the planet's total mass. The core has a radius of as much as 1,289 miles, which is only half the size of Earth's. With the enormous size of Mercury's core, University of Maryland geology professor William McDonough explains the initial formation processes of the Sun. When the newborn Sun was surrounded by a protoplanetary disk, most of the formed metal stayed closer to it. Since metal is heavy, it's difficult to eject it far away with gas. So, the large concentration of metal near the Sun during the early stages of planetary birth could have built up Mercury's core to such a large size. However, there are still likely reasons for the high proportion of metal compared to silicates in Mercury. Scientists speculate that Mercury probably could have been much larger than it is now. However, several hypothetical cataclysms could have prevented its mass buildup. One such cataclysm could have been the influence of the forming of Earth and Venus. Both planets could have formed closer to the Sun, then migrated to their current orbits and taken the building material that was destined for Mercury. On the other hand, Mercury's composition could be the result of an impact on the two planets or the impact of a huge space object, causing it to lose about 1/3 of its mantle. A collision with such massive bodies could have thrown Mercury, which was further from the Sun, into its current unfavorable orbit. impacts from other space objects, the consequences in the form of craters which we see in the images, could have continued to remove the silicate surface of the planet. Nevertheless, all these assumptions are only hypothetical, so we should expect further studies of new spacecraft, such as the Bepi-Colombo mission of the European Space Agency and the Japan Aerospace Exploration Agency, which will focus on the origin of Earth group planets. Still, as much as we would like to learn more about Mercury, it is in fact quite difficult to study up close. From ground-based telescopes, it is extremely difficult to track it at night at the best time to observe it, because of its proximity to the Sun, so it also rises only with a star. The Sun's light can damage optics if you observe Mercury for a long time during the day. Moreover, the small planet is harder to reach even than the farthest planets in the solar system because of the star's gravitational pull and temperature. Therefore, a spacecraft sent to explore Mercury must reach the planet very carefully, which is long and risky and is almost always within acceptable temperature limits for operation. That's why only 2 missions, Mariner 10 and Messenger, were sent to Mercury. Without them, we would hardly know everything we know about Mercury today. Mariner 10 was the first mission to use the gravitational pull of another planet, Venus, to reach a planet. For its maneuvers, the spacecraft used the pressure of solar radiation on its 2 solar panels. Using its abundant instrumentation, Mariner 10 was able to confirm a moon-like crater-covered surface as well as detect the magnetosphere and rarefied atmosphere of Mercury. Moreover, it was Mariner 10 that discovered the planet's large core, in addition to measuring its temperature on both sides. The spacecraft was able to take more than 2,700 images of Mercury, allowing scientists to create a map of nearly half of the planet's surface from those images. In all, the last Mariner made 3 passes over the inner planet 6 months apart. It did not orbit Mercury, but it still managed to make a breakthrough in the study of the planet. The ship's mission lasted about a year. After orbiting the Sun in late March 1975, Mariner 10 stopped transmitting radio signals to Earth. It may still be orbiting the Sun. The Mariner spacecraft Messenger continued its work 30 years later, in 2004. Unlike its predecessor, Messenger not only flew over Mercury but was also the first spacecraft to orbit the planet, which yielded more in-depth and interesting data. The main goals of Messenger were to collect information on the chemical composition of the planet and its exosphere, to study the magnetic field and its sources, and to study geological activity in Mercury's past and the state of its core at the moment. Before entering Mercury's orbit, Messenger made 3 orbits around it, slowing the craft down. From the start of the flight as of 2014, the vehicle was able to take 200,000 photos of Mercury. It managed to take a total of 2,500 pictures. In early 2015, Messenger began to run out of fuel. At the end of April 2015, Messenger finally stalled and crashed into Mercury, forming a new crater on its surface. All in all, the Messenger mission lasted about 10 years. During this period of time, it managed to make many interesting and unexpected discoveries. The most outstanding can be considered a complete map of Mercury. Messenger captured all the craters and basins that were on the planet's surface, so scientists were able to study its geology in depth. Moreover, the spacecraft was able to determine the chemical composition of Mercury. Thus, its surface contains 46% oxygen, 12% magnesium, 26% silicon, 7% aluminum, and 4% calcium. The ship also indicated to scientists that the planet contains a large amount of sulfur with much less iron. This, as well as direct photos of general volcanoes, suggested that Mercury may have previously been volcanically active and even completely covered by a magmatic ocean. When the planet cools after such geologic activity, Heavy elements like iron sink downward, which explains the small amount at the top. The magma ocean phase filled the atmosphere with volatile substances including sulfur, sodium, and chlorine, which evaporate only when exposed to high temperatures. As scientists suggested, the magma also melted the planet's interior and probably the upper, but this was not enough to significantly reduce Mercury's mass. Now the planet is no longer active. In addition, as the planet cooled, it began to shrink, forming cracks and ridges along its surface. In addition to traces of lava eruptions, MESSENGER also found water deposits at Mercury's poles. Water exists there in the form of ice. Despite the high surface temperature, the poles of the planet are not heated by the direct rays of the sun, so the water there always remains frozen. Moreover, it suggests that there may be liquid water inside Mercury under the ice deposit, although this cannot yet be confirmed. MESSENGER also made an unexpected discovery concerning the planet's magnetic field. It turns out it shifted along its axis by 20% of Mercury's radius. Such an anomaly could affect the planet's surface. For example, solar particles would have greater intensity in the south, weathering elements from the surface. Finally, MESSENGER took a 2011 photo from the planet's orbit of the entire solar system except for dim Uranus and Neptune. The previous image was taken back in 1990 by the Voyager 1 spacecraft. Still, the most interesting discovery of both spaceships was the surface of Mercury. So let's take a closer look. Mercury's surface has an interesting topography. Although it's almost entirely covered in craters, it also has almost completely smooth areas as well as ridges and troughs. It's difficult to name the exact number of craters, but at this point we know for sure about 567 of the planet's craters, which are also named after prominent people. Most of them are impact craters, that is, damage caused by an impact with a small cosmic body. Such craters are divided into simple and complex by morphology, such as geological differences like peaks, terraces, several rings. On the surface of Mercury, simple craters predominate, especially in the south. They typically reach sizes of 0.6 to 9 miles and depths of less than 7 miles, or complex craters are slightly less common. They are larger than simple ones, ranging from 10 to 168 miles long and more than 7 miles deep. However, Mercury has the most such topographic lesions than any other object in the solar system. Thus, on the surface of the planet, there are 110 craters with a peak in the middle, when, for example, on the Moon, there's only 17 such craters. Besides, on average, small impact craters, there's another type of these craters as impact basins. They can be as large as 200 miles, or even as large as 963 miles. The rather large numbers on the surface can be explained by the increasing velocity of bodies in solar orbit and a negligible atmosphere. Some of the most famous basins are the Caloris and Rembrandt basins. Caloris is Mercury's largest crater, measuring 963 miles in diameter. In the full image, scientists find that it was previously filled with lava, so you can now see the smooth plains at the bottom of the crater. It is suggested that the object that crashed into the planet and formed Caloris may have also created the chaotic terrain of Mercury, an area modeled with furrows and plains. Further, Rembrandt, the second largest crater, is about half the size of Caloris. It was also probably covered by lava in earlier stages, which is why the area around it is smooth. In addition to these basins, Mercury has several other interesting craters. For example, the basin Thick is the oldest crater on Mercury. It may be over 4 billion years old. It also has the darkest place on the entire planet, covered in particles ejected by a volcano. There are also special, rare types of craters on Mercury. These include elliptical, polygonal, and ghost craters. All of these types have different mechanisms of formation. For example, an elliptical crater is formed because of a low velocity and large volume of the space body. Such craters are about 2 to 4% of the entire surface. The largest elliptical crater is Finsdottir, 137 miles long. Polygonal, that is, craters with several angles, probably arise because of the structure of the planetary crust and its dilapidation. There's about 33 of these on Mercury. Craters, ghosts, are barely visible because their bottoms are filled with lava deposits, but they are distinguished by ridges along the edges, which have arisen from the rapid accumulation of lava flows. The last interesting type of crater, which can also be clearly seen on the Moon, is a ray crater. Their main feature is the long rays diverging from the crater and having a huge length. For example, the longest lines on Mercury have the crater Hokusai at 2,800 miles. These marks appear because the impact triggers the ejection of subsurface elements that fade over time. So the brighter the line, the younger the crater. Thanks to all these craters, scientists can study the dynamics of the planet's geological activity and, among other things, its age. Thus, young craters are convex, with terraces on the walls, while older craters are very shallow because they're probably filled with volcanic material. Still, for example, while studying crater types and sizes, NASA researcher Caleb Fassett noticed that Mercury was missing craters from 12 to 80 miles. He suggested this may be due to the frequent formation of inner crater plains early in the planet's history. High surface structures like ridges and escarpments are not too numerous on Mercury, only about 100. All the uplands were formed in different periods and under the influence of different mechanisms. For example, smooth ledges were formed during volcanic activity, and ridges and wrinkles were formed during the cooling and compression of the planet. On average, they all reach a height of 0.07 to 0.5 miles. Some high mountain ranges, which incidentally do not exist on Earth, on Mercury can reach up to 360 kilometers in length, like Antagnani Dorsum. Nevertheless, despite the study of Mercury's surface, the history of global compression is still unknown. Another 27% of the planet's entire surface is occupied by almost perfectly smooth plains with few craters. Such plains are found at all latitudes as well as around large basins. 2/3 of them are formed due to volcanic activity, and the rest is probably due to volcanic particle emissions by the Caloris Basin. The last geological oddity of Mercury, which is not observed anywhere else, is its hollows. They were noticed by Mariner 10, but Messenger made clearer images, so it is awarded the first discovery. They are shallow depressions without edges and with flat bottoms that occupy about 0.08% of the planet. In most cases, they are inside impact craters. Scientists speculate that they are much younger than Mercury and are formed by the loss of volatiles from the surface. The process of hollow formation has not stopped, so the surface of a planet may change over time. So scientists believe that 99% of Mercury's surface could be completely transformed in 25 million years. Mercury is a very valuable planet to study the dynamics of surface changes, as well as the mechanisms of the formation of different landforms. Therefore, in 2018, a new spacecraft was sent to observe the first planet of the solar system, which will continue the mission of the previous two, Bepi Colombo. It consists of two separate spacecraft that will observe Mercury from far and near at the same time. Its primary mission, to answer the questions that Messenger has raised. That is, Bepi Colombo will investigate in more detail the origin and causes of magnetic field displacement, water deposits at the poles, cavities, and the mechanisms of their formation. In 2025, Bepi Colombo should enter Mercury's orbit and begin its main work. Hopefully, this new study will be able to solve most of the mysteries of this planet. which will have good implications for our understanding of the history of the solar system. We're used to thinking that life can originate only on planets similar to our Earth, exoplanets close to the central star. However, what if we say that such exoplanets are probably not the only candidates for the emergence of life? Perhaps small icy satellites distant from the Sun could also be home to living organisms. Today we're going to tell you about Saturn's two satellites, Mimas and Enceladus, and how life could potentially thrive on seemingly lifeless satellites. First, let's take a closer look at Mimas. Mimas was discovered relatively recently in 1789 by the English astronomer William Herschel. Mimas is one of the smallest satellites of Saturn, with a diameter of only 248 miles, about 1/4 or a quarter of our Moon. Mimas consists largely of water ice, so the surface is very cold. The average temperature reaches about -328 degrees Fahrenheit. It's also very close to Saturn. The average distance between the satellite and the gas giant is 115,000 miles. This proximity is probably caused by the migration of Mimas. By the way, this event also explains one oddity of Saturn's rings. Have you ever noticed that Saturn's rings are separated by a line? This line is called the Cassini division. Researchers from the Paris Observatory suggest that Mimas may have migrated closer to Saturn in the past, thereby clearing this line of ice and dust particles. Scientists estimate that Saturn would need another 40 million years to reclose the 4,500-kilometer line. Moreover, Mimas is in resonance with the other satellites, Enceladus, Thepai, and Diona. That is, the closer they are to each other, the faster they move in their orbits and accordingly slow down when they move away from each other. This relationship stretches the orbit of Mimas to an almost elliptical shape, which supports the idea that life could exist on the satellite, but more about that a little later. However, of greater interest is the surface of the satellite. Mimas is almost entirely covered by huge craters. Most craters are about 20 to 40 kilometers in diameter in both hemispheres, but all of them pale before the main distinguishing feature of Saturn's satellite, the giant Herschel crater in the northern part of Mimas, and it gives a resemblance to the famous Death Star. The size of this crater is about 80 miles, which of course may not seem very impressive when compared to Earth. But for small Mimas, it's almost 1/3 of its diameter. It was not William Herschel who discovered the crater, but the Voyager spacecraft in 1980. Nevertheless, this does not mean that the crater appeared recently. Its age is estimated at 4 billion years. Scientists suggest that the space body that crashed into Mimas and left the crater may have almost completely destroyed the Moon. Moreover, in the middle of Herschel crater, there's a mountain 6 kilometers or 3.5 miles high, which is slightly smaller than Everest, which shows how strong the impact was. Nevertheless, such a large cosmic body could not have been limited to the external changes of the satellite. One of the most noticeable effects of the collision is probably the very strange surface temperature of Mimas. The temperature inside Mimas is expected to flow smoothly from the hot core to the cold surface, like on ordinary planets, but Cassini's temperature analysis has baffled scientists. It turned out a small part of the satellite on the left, which resembles the Pac-Man shape, is hot, while the rest of the surface is cold. Remarkably, Herschel's crater is also much warmer than the rest of the surface. The culprit is probably just this unknown body. Researchers speculated that the impact might have melted the ice on the surface. The thawed water could have frozen instantly, causing such a temperature difference. However, the top layer of Mimas remains intact. the other hand, researcher Carly Hubbard has pointed out that such strange temperatures may be caused by irradiation, by charged particles that are captured by Saturn's magnetic field, as confirmed by data from Cassini. So far, there's no concrete answer to this question, so perhaps further expeditions can bring us closer to unraveling this temperature Pac-Man. Now consider Saturn's other satellite, Enceladus. In terms of its characteristics, it doesn't seem to be very different from Mimas. Was also discovered by astronomer William Herschel. Enceladus is only about 100 kilometers larger in diameter than Mimas, and its average temperature and composition are not at all different, except that its density is higher than the latter. Just like Mimas, Enceladus has an elongated elliptical orbit due to the interaction with the Iona, and it's also heated by attraction to Saturn. However, Enceladus has a very smooth and young surface, unlike Mimas. It also has craters up to 22 miles on its surface, but very few, more dominated by depressions and ridges that can be seen almost all over the Moon's surface. The abundance of such landforms may indicate different tectonic activity, like an earthquake when tectonic plates compress. Moreover, another interesting similarity between Enceladus and Mimas is their influence on Saturn's rings. True, Enceladus did not harm them as probably Mimas did, but rather created them. In addition to the bright rings which are very close to the gas giant, there's another ring, Ring E, which is less clear and is for 112,000 miles from the center of Saturn, occupying approximately 186,400 miles wide. So how could such a small planet create such a huge ring? This is where some serious differences between Enceladus and Mimas begin. First, let's look at the surface of the Moon. Unlike the seemingly lifeless Mimas, Enceladus emphasizes that it's an icy satellite. It's almost entirely covered with pure fresh ice dusted with something like snow. By the way, it's this feature of Enceladus that allows it to reflect almost all the light that falls on it, which only makes its surface colder. But still, how could snow appear on the satellite? Does it have an Earth-like atmosphere? In fact, snow on Enceladus forms inside. The surface of Enceladus, also like Mimas, has one feature, but this time it's not a giant crater, but long, parallel cracks at the South Pole, which are dubbed tiger stripes. Flying near Saturn in 2005, Cassini detected strange activity in these tiger streaks. Pillars of water vapor were flying out of them. Moreover, Cassini also noticed that the Moon wiggled as it rotated. For scientists, this meant only one thing. There is also an ocean lurking under the ice column of Enceladus. It is these ice particles that fly out of the ocean depths at a speed of 800 miles per hour. And they cover all of Enceladus and also form a huge ring for Saturn. By the way, probably because of the water ejections inside, Enceladus has such a smooth surface. Enceladus also has volcanoes, but they spew water rather than lava, smoothing the satellite's landscape. However, Enceladus is very small. Shouldn't it be depleted at this rate of emissions? Well, astronomer Phil Plait thinks it'll take about 9 billion years, which is twice the current age of the solar system. So it won't disappear for a long time. So where did these amazing stripes come from? According to a study by Douglas Hemingway, the ice at the pole is thinner, so the cracks appeared there due to the gravitational interaction of Saturn and frozen water, which increased the pressure on the ice wall. In addition, thanks to these tiger stripes, Enceladus can keep its ocean in a liquid state, which is necessary for the origin of life. Moreover, the Moon has an atmosphere that's largely composed of water vapor, and also small amounts of nitrogen, carbon dioxide, and methane. Interestingly, the Moon also probably has a metallic core, and due to its oddly porous shape, it can heat the satellite's ocean, making it even more suitable for organisms. Thus, Enceladus may be hiding an entire life under a layer of ice. Nevertheless, if Enceladus and Mimas in general are similar, then why is the ice on Mimas not melting at all, although Enceladus has clearer traces of an internal ocean? In addition, thanks to its more elongated orbit, Mimas should heat up much more than the same Enceladus, but it remains completely frozen. This temperature weirdness has led NASA scientists to even come up with cases to test theories that explain the frozen water on the satellite that should also justify partial water in geysers on Enceladus. Researchers from the University of Warsaw, they believe that such a paradox could hypothetically be caused simply by different periods of heating of the two satellites by Saturn's gravitational pull. Thus, Enceladus is much denser than Mimas, so it could be heated much longer, while Mimas, due to its small size, could cool down very quickly. Moreover, in order not to lose much heat, the satellite needs to enter into resonance with another body as soon as possible. However, Mimas merged with Tophaia too late, when it had already cooled down. So, Mimas can be considered a frozen block of ice that is unlikely to melt, so no life is possible on it. Not exactly. Indeed, for a long time, scientists considered Mimas to be a lifeless moon, but a recent observation has forced the scientific world to reconsider its attitude. In 2014, Cornell University researcher Radwan Tajedin discovered that Mimas wobbles back and forth as it rotates, and this unusual behavior of the planets is explained by a weirdly shaped nucleus or by some kind of internal activity. But what could be inside this small satellite? Scientists think that under the dozens of kilometers of ice crust of Mimas, there may be an ocean, just like on Enceladus. Scientists at Southwestern Research University last year found that Mimas is capable of generating enough heat to keep the ocean inside itself. Apparently, however, it's not enough to melt the thick layer of ice. Nevertheless, according to observations, the ice shell of Mimas began to thin after the appearance of a huge crater. Therefore, it's possible that Saturn's satellite may only be an incipient oceanic world. Moreover, Radwan Tajedin suggests that the elongated elliptical orbit of Mimas, which allows for better heating of the satellite, may also support the ocean. Thus, Mimas and Enceladus reveal to scientists the possibility of similar ice space bodies with hidden oceans, and most importantly, the possibility of life development even on seemingly empty and inactive planets. The ocean is practically the basis for the origin of life, so could Mimas and Enceladus be potentially inhabited? Let's try to figure that out. However, for starters, could ice planets become habitable because it's too cold for vital processes? Astronomer Adiv Paradise thinks that Earth may have been a cold water planet at its stage of development, which is exactly what probably started life as we know it. However, such planets also probably need certain warm areas to support life and carbon dioxide. Therefore, ice planets should probably not be ruled out as theoretically habitable. In addition, there's more than one cold planet in our solar system on which life is possible, and Mimas and Enceladus may also belong to them. You already know that Enceladus definitely has an ocean. However, it's important to note that its geysers and particles within the E-ring of Saturn hint that the ocean is warm and probably has hydrothermal vents deep. That is, it could be considered ideal for the development of microbial life. Moreover, Cassini found that these geysers contain the chemical elements necessary for life: oxygen, hydrogen, and various carbon compounds including methane, which is the result of microbial life. A team of scientists from the University of Arizona and the University of Paris, after studying the gas emissions, believe that microbes could probably exist in the ocean of Enceladus, just like on Earth, which moreover does not need sunlight. Saturn, by the way, can send various compounds into the ocean of Enceladus, and probably including Mimas. Also, as we noted, Enceladus has an atmosphere with important chemical elements. Although we won't be able to breathe on Enceladus, this moon could still probably be home to single-celled life. But what about Mimas? Unfortunately, this moon has not been of much interest to scientists, so much about it remains unknown. Nevertheless, the liquid ocean is a very significant factor in the origin of life. Therefore, it is possible that the ocean of Mimas may also contain the same different elements for the development of organisms that exist on Enceladus. Moreover, the ice thickness on Mimas is completely similar to that on Enceladus, meaning that internal activity could melt it. However, unlike Enceladus, Mimas, as you know, has a strange temperature distribution, and probably because of this, we don't see water geysers and therefore don't know what compounds the likely ocean holds. However, this does not necessarily mean that life on Mimas is impossible. Scientist Alyssa Roden suggests that the lack of tiger bands can be explained by the fact that the possible ocean formed relatively recently on a cosmic scale. In addition, she noted that its elongated orbit allowed Mimas to be well heated, so it probably has a warm liquid ocean, meaning it's probably heated not only by attraction to Saturn, but also by internal sources like Enceladus. Nevertheless, Mimas has no atmosphere at all, which may reduce the chances of life, but not eliminate it. Mimas and Enceladus were a real boon for planetary science. They've opened the scientific community to icy planets as likely candidates for life. They've also added more work for scientists by showing that life may not only be worth looking for on planets like our Earth. Many of us have grown up with the idea that Earth simply revolves around the Sun, which stays still in space. But in reality, the big picture is much more complicated and fascinating. As we delve deeper into how Earth actually moves through the galaxy, we'll find that our planet not only revolves around the Sun, but is dashing through space at an incredible speed at the same time, along with our entire solar system. But what if we told you that this movement could be connected to some of the universe's greatest mysteries? For instance, scientific hypotheses suggest that Earth's movement through the galaxy may expose us to cosmic rays, which would cause genetic mutations and contribute to the mass extinction of life. Furthermore, changes in our planet's orbit around the Sun may affect the environment, which could lead to catastrophic changes, such as another ice age. Understanding how our planet moves through the universe, we can appreciate our place in space more. We may even find clues to answer some of the bigger questions, such as how our galaxy formed and what the future holds for us. For starters, imagine that you're in an airplane that's flying at a constant speed and altitude. While in it, you won't be able to tell how fast you're going or even if you're moving at all. From your point of view, it seems that only the world outside is moving. However, someone on the ground watching a passing aircraft will perceive its movement relative to their own stationary position. This outline, which was first outlined by Galileo Galilei in his 1632 book, The Dialogue Concerning the Two Chief World Systems, to express what we now call Galilean relativity or Galilean invariance. It's the concept that defines the absence of an absolute frame of reference for motion. And even when there are several valid frames of reference, we still need to choose the most relevant one, depending on the situation. So how does this fit in with the idea of Earth's movement and the solar system as a whole? First, we need to determine the observation point. When viewed from within our star system, as we all know, the planets orbit the Sun. However, with a broader consideration of things, we can see a completely different picture. The solar system is constantly moving in a spiral through the expanse of our galaxy. One of the best-known examples of relative motion within our solar system is Earth's revolution around the Sun. Earth's orbit is not a perfect circle, but rather an ellipse, with the Sun as one of its foci. That means that at some points in its orbit, Earth is closer to the Sun than at others. When Earth is closest to the Sun, it is said to be at perihelion, and that the farthest point in its orbit in relation to the Sun is known as aphelion. These 2 points occur at regular intervals. Earth reaches perihelion around January 3rd and aphelion around July 4th, which is evident with the seasonal changes of the weather. You know the usual depiction of the solar system, with the Sun in the center and the planet revolving around it. Well, that's not a completely accurate representation of the movement within our planetary system. You see, the planets don't just revolve around the Sun, but they also pull it in, causing it to shift. For example, the gas giants Jupiter and Saturn have a particularly strong gravitational influence on the Sun and Earth, which causes small changes in the shape and orientation of their orbits. When Jupiter and Saturn are even remotely lined up, they have a significant effect on all the bodies in the solar system. This effect is known as the perturbation of the outer planets. Over time, these subtle changes in Earth's orbit can accumulate, leading to long-term changes in the planet's climate and overall environment. These changes are known as Milankovitch cycles. One of the aspects of the Milankovitch cycles is the change in the tilt of the Earth's axis, which shifts from about 22 to 24.5 degrees in a cycle of about 41,000 years. This change in the planet's tilt affects the amount of solar radiation reaching different parts of the Earth's surface, which in turn can affect the timing and intensity of glaciation periods, ice ages. Based on these cycles, some scientists predict that in the relatively near future, a new ice age may begin on Earth, spanning across tens of thousands of years. However, it's important to note that the effects of an anthropogenic climate change are currently suppressing Earth's natural climate cycles, making it difficult to predict the exact timing and intensity of future ice ages. Let's face it, Earth's movement pattern within the solar system is very complex. However, its movement through the galaxy is even more intricate. The Milky Way galaxy is a massive and complex system which includes a vast amount of stars, gas, and dust, spanning across over 100,000 light-years in diameter. One of the most exciting aspects of our galaxy is its rotation. Like a huge spinning windmill, the galaxy's spiral arms trail along as it spins. This rotation makes the stars and gas in the galaxy move in circular orbits around the galactic center. Earth is located in one of the spiral arms of the galaxy, about 25,000 light-years from its center. In the solar system, there are only a few bodies that have to be taken into account in terms of gravity, and the Sun is the dominant celestial body in this gravitational field. In contrast, the Milky Way's gravitational field has no dominant object. Instead, everything revolves within the total gravitational fields of everything else. This makes tracking the motion of the galaxy's components a difficult but rewarding task, allowing us to learn a wealth of information about the complex structure of our galaxy. Just as Earth orbits the Sun revolves around the center of the Milky Way galaxy at a speed of about 143 miles per second, completing one orbit in almost 230 million years. This cosmic journey takes the Sun, and therefore also Earth, through different regions of the galaxy, and introduces us to different cosmic environments. Interestingly, the stars in the inner regions of the galaxy move faster than the stars in the outer regions due to the fact that the parts closer to the center of the galaxy have more mass, and therefore a stronger gravitational pull. This difference in speed is akin to the way planets closer to the Sun move faster along their orbits than those farther away. Determining the speed of the Sun relative to the center of the galaxy involves searching for new, young stars that have only recently formed and are therefore still in their birth orbit. Next, taking an average of how these stars move relative to us, we can deduct that the Sun is drifting forward at the speed of about 3.1 miles per second, in towards the galactic center at a speed of about 5 miles per second, and up and out of the galactic disk at about 4.4 miles per second. This small, peculiar motion has huge implications for the path that the Sun and solar system take through the galaxy. The orbit of the Sun around the center of the galaxy is not perfectly circular either. Instead, it follows a slightly elliptical path, oscillating above and below the galactic plane. It completes a full oscillation approximately once every 60 million years. This movement is influenced by the gravitational pull of other stars, gas clouds, and dark matter in the galaxy. We're currently several dozen light years above the middle plane of the galactic disk, although it's difficult to determine exactly where the center is. Since there is more matter below us than above us, the gravity of the disk slows the upward movement and, in a few million years, will be about 300 light years above the center of the disk before our upward movement slows to a complete halt and we begin to descend. The vertical oscillation is more than just a peculiar phenomenon. Some astronomers support the Shiba hypothesis and believe that it can be directly related to mass extinctions on Earth, since the center of the disk is a more dangerous place for the solar system due to the higher density of stars and the radiation they emit. The motion of the galaxy's spiral arms is not yet fully studied, but is theorized to be caused by a combination of factors. One of them is the gravity of other galaxies in the local group, the cluster of galaxies that includes the Milky Way. Another factor is the existence of density waves, which are believed to propagate across the galactic disk like ripples in a pond. These waves can force stars and gas in and out of the spiral arms, potentially affecting the environment and living conditions on Earth as we pass through these regions. For example, as the Earth passes through an area of higher density, there may be more cosmic rays and other high-energy particles reaching the surface of our planet. This could have implications for our climate, atmospheric chemistry, and even the evolution of life on Earth. As we discussed previously, the Sun is not stationary. It moves through the Milky Way galaxy, dragging Earth and the other planets along with it. However, the Sun is not the only moving object. All other stars in the galaxy are also in motion. The motion of the stars can be defined in terms of their proper motion, which refers to the star's visible motion across the sky over time. Proper motion is caused by the movement of stars in space relative to the Sun. It's usually measured in arcseconds per year, which is the angular displacement of a star in the sky over the course of a year. The concept of proper motion allows astronomers to track movement of stars over time and study their movement and position relative to each other. This is important because it helps us get a better grasp of the structure and dynamics of the Milky Way. Now, let's take a look at the movement of Earth relative to the nearest stars. Due to Earth's movement around the Sun, the apparent positions of nearby stars in the night sky change slightly over time. This effect is known as parallax. It happens due to the fact that at different times of the year, Earth is in a different position in its orbit, resulting in slightly different viewpoints for nearby stars. The amount of parallax observed for each particular star depends on its distance from Earth. Stars that are closer to Earth will display more parallax than those that are farther away. astronomers can use the amount of observed parallax to determine the distance to nearby stars, which is an important tool for understanding the size and structure of a galaxy. In addition to parallax, our perception of the night sky is also affected by the proper motion of nearby stars. Over several years or decades, the position of nearby stars can change markedly due to their own movement in space. This means that the constellation patterns we see today will look somewhat different in the future and would have looked somewhat different in the past. The effect of proper motion is especially noticeable for nearby stars that have a large proper motion, or in other words, the fast-moving stars. Now that we have a breathtaking picture of the way our solar system actually moves through the galaxy, one question remains. How do we move through the universe as a whole? As it turns out, the Milky Way is not alone in its travels. Our galaxy is constantly pulled by the gravitational fields of various masses surrounding it. We're currently racing towards the Andromeda galaxy at the speed of a couple of 100 miles per second. But that's not all. The Milky Way is part of a group of galaxies called the Local Group, which includes more than 54 other galaxies, including our nearest neighbor, the Andromeda galaxy. The Local Group, along with many other groups and clusters of galaxy, is moving towards a mysterious superdensity and a supercluster of galaxies known as the Great Attractor. The Great Attractor is a region of space about 150 million light-years away, and its gravitational attraction is so strong that it influences the motion of galaxies within hundreds of millions of light-years. As a result, the Local Group is pulled towards the Great Attractor at a speed of about 373 miles per second. However, this movement is still not the last of Earth's movement in the universe. Our entire universe is expanding, and as a result, all the galaxies in it are moving away from each other. This expansion is not a movement in space, but rather a stretching of space itself. The universe is expanding at an accelerating rate, and as a result, the distance between galaxies increases over time. Despite all of this motion, we can still use the cosmic microwave background radiation as a frame of reference for determining our speed relative to the rest of the universe. This radiation, which is the residual heat of the Big Bang, permeates the entire universe and is almost uniform in all directions. By measuring tiny variations in this radiation, scientists have determined that Earth and our entire solar system are moving through the universe at about 229 miles per second relative to the cosmic microwave background radiation. At this point, it's no longer a stunning revelation to anyone that Earth is far from stationary, but rather a tiny but important part of a complex system of celestial movements. The pronounced complexity of the motion of our planet is an impressively complex phenomenon. First, our planet gracefully orbits the radiant sun as it has for billions of years. But that's just the tip of the iceberg. The solar system, which our planet is a part of, also moves through the vast expanses of the Milky Way galaxy, rushing forward at incredible speed and leaving a corkscrew pattern behind it. And that's still not all. The Milky Way is part of a galactic congregation known as the Local Group, which includes a number of nearby galaxies. And together, they perform this cosmic dance as they move toward the mysterious gravitational force known as the Great Attractor. And this tug-of-war causes the Local Group to dash through space at several hundred miles per second. But even that is not the end of the story. The universe itself is expanding, a fact that has been known since Edwin Hubble's groundbreaking discovery in the 1920s. This expansion means the galaxies are moving away from each other at an astonishing rate. In conclusion, Earth is not just a rock flying through space. It's part of a grand scheme, a web of cosmic movements, both intricate and awe-inspiring. We're just a tiny speck of dust in the vastness of this universe. But the movement of our planet is an integral part of the puzzle that is space. In 2021, the James Webb Space Telescope, or JWST, was launched from Kourou, France, to study at Lagrangian point L2 the cosmic bodies in distant galaxies around us, which can help us learn more about the birth of the universe. Equipped with large mirrors and revolutionary instruments, James Webb was able to make several important discoveries for the scientific world in just 1 year of the mission, including such complex cosmic processes as star formation and their death. Today you'll learn about JWST's most remarkable discoveries to date, from the first detailed image of a cluster of galaxies to a new exoplanet. One of Webb's first images was of the galaxy cluster HES-MACS 0723, 4 billion light-years from Earth. Was not a discovery. The cluster was first explored by Hubble. However, thanks to its cameras, Webb was able to provide a very detailed image, revealing to scientists hundreds of previously unseen small galaxies. Interestingly, Webb made this image in just 12 hours, when it would have taken Hubble several weeks. Webb's photos will allow scientists to study young galaxies before they merge into larger spiral galaxies. For example, a study led by Rohan Naidu of Harvard University indicates that some galaxies there may have formed in as little as 300 million years after the Big Bang. In addition, scientists noticed elongated galaxies that also appeared simultaneously in different places. According to the research of astronomer Massimo Pascal, the cause of stretching may be the gravity of the galaxy cluster, which distorted the light, causing galaxies to appear in different places. The scientist also noted the elongation of SMACS 0723. It could be caused by its collision with assumingly another galaxy cluster. The next important image of Webb was a rare ring galaxy, the Cartwheel, 500 million light-years away. It was discovered back in 1941, but a detailed image was only obtained now. Its strange appearance reminding us of a wooden carriage wheel with the circle in the center and diverging spokes, probably formed as a consequence of a high-speed collision between two galaxies over 400 million years ago. Therefore, it's likely that the Cartwheel galaxy looked just like our Milky Way before the collision. Moreover, Webb discovered that the core of the wheel contains a large amount of hot dust, and that the brightest regions emanating from the center contain many young stars. That is, as the galaxy expands, it pushes dust and gas outward, forming stars. The Cartwheel galaxy is still transforming after the collision, so further observations by Webb could reveal more of the mysteries of this galaxy and also look at the star-forming process. In July of 2022, Webb captured the last moments of a dying star that had been emitting gas and dust for several millennia, forming the South Ring Nebula. This nebula, only 2,000 light-years away, was also explored by Hubble, but it only captured one star there, very bright in the infrared. As the emission continued, the star, which was 3 times the size of the Sun, shrank significantly, turning into a white dwarf. Because of this, the star could not shine brightly. Scientists then concluded that all the material ejected by the star must have formed a dust disk that would have glowed when heated. Such a dust disk could only be created by another star. Moreover, Webb noticed another oddity. The nebula has lines along its edges. It's unlikely that the dwarf itself could have created such patterns. Thus, Macquarie University astrophysics professor Ursula DeMarco believes that the white dwarf may have several companion stars that scattered all the material and created a disk around the central star. Finally, Webb confirmed that there is a second young star near the dwarf, although no other stars are visible. Scientists speculate that they are either too dim or have already been absorbed by the central star. Therefore, Webb's study will help scientists not only learn more about this association of stars, but also to study the chemical composition of the ejected material. In addition to the death of the star, Webb was able to capture its birth. Webb succeeded in capturing the bright clouds emitted by the newly formed star, L1527, at a distance of about 460 light-years. The star emits layers of dust and gas in different directions, so the appearance of this nebula resembles an hourglass. The color of the clouds is determined by the thickness of the dust, an orange color where the dust is denser and vice versa. The thinner the layer, the bluer the color would be. Scientists estimate that this star is only about 100,000 years old, when a star is formed about 10 million years or more. Also, NASA researchers believe that L1527 is already approaching the generation of its energy through nuclear fission, so it will soon be able to ignite on a cosmic scale. Moreover, the barely visible line that crosses the clouds is a protoplanetary disk, and it is the size of our solar system. Therefore, it is likely that planets could form around L1527, just as in our system. This in turn will not only allow us to observe what the solar system looked like when it formed, but also to consider these exoplanets as possibly inhabited. Another distant Kill Nebula was the target of James Webb's research. The Kill Nebula contains a region of star formation NGC 3324, the edge of which Webb captured in detail. The rock-like part of the nebula is actually hot, ionized gas and dust. Amid this nebula, Webb was able to capture with its cameras hundreds of previously hidden newborn stars. Moreover, the telescope also detected thin jets of hydrogen erupting from the top of the nebula. Such columns could probably indicate an active period of star formation. Such an event is very rare, and it lasts only up to 10,000 years. This discovery is a new step in the study of star formation and its effect on nearby planets and the entire nebula. In addition to the Kill Nebula, Webb studied another nebula that could also bring scientists closer to a better understanding of star formation. The Pillars of Creation Nebula is about 6,500 light-years away in the Eagle constellation. In its huge columns of dust and gas, 4 to 5 light-years long, Webb discerned many young stars that are just forming. Take a look at the nebula's second pillar. The top of it is reddish and looks like lava. This means that there are stars in this area that are emitting jets during formation, which means they are estimated to be 100,000 years old. By the way, scientists also noticed that there should be more stars in this image. The fact is that stars have recently finished their development. They had got rid of the dust surrounding them, so it's difficult to see them in the mid-infrared. But nevertheless, the information from James Webb will be enough to investigate how stars form and emerge from these dust clouds. Webb's next discovery is of even greater interest to scientists. This time it is not a nebula, but the brown dwarf glass JWST BD1 at a distance of about 2,000 light-years from Earth. Brown dwarfs are quite rare and dim and also have some of the characteristics of a planet. That is, they're not massive enough to synthesize hydrogen and emit starlight, but they also have an atmosphere like a planet, with the probable presence of water molecules in it. So studying why a star has so little mass will help scientists learn more about the boundary between planets and stars, and how they form. Now, back to our dwarf. Very little is known about glass JWST BD1 at the moment. It is about 30 times larger than Jupiter and has a temperature of about 720 degrees Fahrenheit. Brown dwarf researchers led by Mario Nannino said that further observations are needed to learn the star's chemical composition and properties. But in addition to glass JWST BD1, Webb was also able to study the previously discovered brown dwarf, DHS 1256-1257b, specifically its dust clouds. DHS 1256-1257b is relatively close, 72 light-years away, so Webb was able to examine its atmosphere in detail. It found many important chemical elements there, including water and carbon dioxide, as well as a cloud of silica particles. Thus, Webb was able to bring scientists a little closer to understanding the structure of dwarfs and exoplanets. The first exoplanet that Webb captured was the gas giant HIP 65426b. This young exoplanet 385 light-years away was discovered back in 2017 by a ground-based telescope. However, the study of the planet was complicated because it was quite difficult to get a detailed image with short infrared light waves, especially because of the large number of bright stars. For example, the star HIP 65426, around which the exoplanet orbits, is 10,000 times brighter than it. Nevertheless, Webb's cameras took the first direct image of the exoplanet during its mission. HIP 65426b is 100 times farther away from its parent star, so the telescope was able to spot the planet. Although Webb did not get a closer look at HIP at 65426b because of the enormous distance, the images will help scientists learn more about the planet and the system as a whole, as well as opening up the possibility of taking pictures of other distant exoplanets. Another of Webb's first scientific mission targets was the WASP-39b exoplanet. It was previously observed by the Hubble and Spitzer telescopes, but Webb was able to provide an almost complete characterization of its atmosphere. WASP-39b is a gas giant slightly smaller than Jupiter with very low density, so life is unlikely to be possible there. It is about 700 light-years away from us and orbits a G-class star, WASP-39, similar to our Sun, but which slightly smaller and cooler than our star, probably due to its older age. However, WASP-39b is the closest planet to the central star. It orbits at a distance of 4 million miles or 7 million kilometers, which is 8 times closer than Mercury to the Sun. That's why temperatures there are very high on average, 1600 Fahrenheit, and with its mission, Webb confirmed the presence of water vapor, sodium and potassium in the atmosphere, which had been detected by previous studies. This year, Webb recorded sulfur dioxide, oxygen, methane, and for the first time on exoplanets, carbon dioxide, which amazed scientists. Sulfur dioxide results from a chemical reaction when it interacts with starlight. And by the way, on Earth, the ozone layer is formed as a result of the same interactions. In addition to the presence of oxygen, according to Kazumas Ono, a scientist at Santa Cruz University, it may indicate that the planet is migrating toward its current orbit. Such reactions have not yet been observed on other exoplanets, so WASP-39b offers scientists an opportunity to study the formation of atmospheres on exoplanets and the history of the formation of the planets themselves. Finally, in January 2023, it was revealed that Webb had been able to join the ranks of discovered exoplanets with its find. At a distance of about 40 light-years from Earth, Webb, observing a red dwarf, noticed how the light from the star covered the object orbiting it. In just 2 rotations or 4 days of the object around the star, Webb accurately determined it was a planet. Thus, exoplanet LHS 475b became the first planet discovered by Webb. Making a direct picture of the planet is not something Webb has had success with yet. However, researchers have already been able to give the first characteristics of LHS 475b. At this time, we know that this exoplanet is almost entirely the size of Earth. It has a rocky composition and has a fairly high temperature of about 100 degrees Celsius, more than the Earth. It's not yet been possible to determine whether it has an atmosphere. However, if an atmosphere is detected, a group of scientists led by Jacob Lustig-Jaeger believes it could be similar to Venus. Still more research is needed to establish whether there is an atmosphere there and perhaps even whether life could exist there. The James Webb Telescope has reached its research point in a year. Together with the scientists, they've about 9 more years of work ahead. Webb's main missions are the study of early galaxies, star formation, and the in-depth study of exoplanets and planets in our solar system. Shortly, Webb will probably study the TRAPPIST-1 system, some planets of which may be inhabited. Moreover, Webb will focus on studying the atmospheres of Mars, Pluto, Jupiter, and Kuiper Belt objects, which could provide more information about the origin of the solar system. Another mission for Webb is to investigate the sources of water in space objects. To do this, Webb will study Jupiter's icy satellite Ganymede, where there could be an internal ocean. This could also help further studies of icy ocean satellites like Enceladus, Europa, and possibly Mimas. Therefore, we expect that Webb will be able to make many discoveries over the years that will change our understanding of the universe.